Hello, my name is Daniel Droege. I am a fourth-year PhD candidate at UC Santa Cruz performing research in the Johnstone Lab. I work on investigating small molecule antidotes for carbon monoxide poisoning. Carbon monoxide poisoning results in over 50,000 emergency department visits every year in the US and is one of the most common forms of poisoning worldwide. Oxygen is still the accepted treatment for carbon monoxide poisoning, but depending on the amount of carbon monoxide inhaled and the time it takes to receive treatment, oxygen treatment may not be enough to prevent death or long-term damage. Despite the great need, there is no established antidote for carbon monoxide poisoning. I aim to use the seminal work done on heme model compounds and biologically relevant carbon monoxide scavengers depicted here to design an antidote for carbon monoxide poisoning. Currently, I am investigating novel meso-substituted porphyrin scaffolds to discover an antidote for carbon monoxide poisoning. The synthesis of this scaffold is depicted here on the left. The Lindsay method was used to generate an aryl meso-substituted porphyrin core. Aryl aldehydes featuring a 2,6 substitution pattern permit modulation of the bulk of the carbon monoxide binding pocket, either early in the synthesis or at a later stage via palladium catalyzed coupling. Installation of the 4 sulfonate groups imparts water solubility at physiological pH and inhibits membrane permeability. The carbon monoxide binding ability and half-life of our complexes were investigated using UV-vis spectroscopy, IR spectroscopy, and X-ray crystallography. A preliminary demonstration of efficacy was performed using both pure hemoglobin, shown here on top, and purified red blood cells, shown on bottom. In the case of red blood cells, a suspension of the cells was treated with sodium dithionite and then sparged with carbon monoxide, generating carboxyhemoglobin. The carboxyhemoglobin containing red blood cells were then washed with phosphate buffer solution and centrifuged to remove any excess dissolved carbon monoxide. The carboxyhemoglobin containing red blood cells were then dosed with our iron porphyrin compound. UV-vis spectroscopy of the suspension confirmed the presence of carbon monoxide-bound form of our iron porphyrin and the loss of carbon monoxide from hemoglobin. Finally, I have demonstrated the synthetic versatility of our porphyrin scaffold. Depicted here are some of the derivatives I have synthesized and some surface models generated from X-ray diffraction data. I am starting to explore derivatives of our compound to uncover greater stability, selectivity, and oxygen tolerance needed to function as carbon monoxide poisoning antidotes. In summary, I have developed a small molecule platform for carbon monoxide sequestration that could have applications in the development of a carbon monoxide poisoning antidote. A proof of principle compound demonstrated the viability of the synthetic strategy. Upon reduction, our compound has an affinity for carbon monoxide, an ability to remove carbon monoxide from carboxyhemoglobin, and the capacity to sequester carbon monoxide from poisoned red blood cells. This activity is performed without any damage to the cells. Thank you to my lab and the ARCS Foundation for support, and thank you for your time.